Hi, and welcome back to Stats Online. So today we're talking about hypothesis tests of a single population mean, and specifically we're going to do some examples to show you the decision rules for a two-tailed test. And so the question is, how do we decide whether or not to reject a null hypothesis? In a previous lesson we laid out the two possible decisions you could make, which is failing to reject a null or rejecting a null. And today we're talking about the decision rule to how do you actually make this decision, okay? What underlies that decision? And then we'll go through some examples from start to finish. And so significance levels and critical values are going to play a role. Now, you've seen these terms before in the construction of confidence intervals, and lo and behold, a confidence interval can provide the same level of information as the rejection region approach I'll develop today for implementing a hypothesis test. Okay, so you actually, if you can construct a confidence interval around a sample mean, you can conduct that hypothesis test of a mean, as long as it's two-tailed. All right. So how do we decide whether to reject a null hypothesis? Well, the first step is we're estimating mu, the unknown population parameter mu, using a sample mean x bar. Okay. And then we're going to be comparing that sample mean x bar with a null value, a hypothesized value of that unknown population parameter, right? A numeric value. So we're going to have x bar a number, we're going to have our hypothesized number, we have to compare them. Now we know that we've only taken a single sample, okay? And so x bar is likely going to differ from the true population mean because of sampling error. And so the sample data must convince you, okay, that HO is wrong. So x bar has to be far enough away from our hypothesized value for us to reject this null hypothesis. All right, and so the question is, what's a sizable difference? And to motivate that, consider this sampling distribution, assuming that HO is true, assuming that this notation, right, mu sub naught, this is the hypothesized value of the population mean. So assuming that's true, and with a population standard error sigma sub x bar, let's look at this distribution of sample means. Here's the question: how often will sample means fall out here? And you can see that this is 3 standard errors below the mean. Well, by the empirical rule, we know that this should be about 0, right? And if you go to the table, the z table, you can get a more precise 0.0013. All right. So about 0, but it becomes positive in that third decimal place. So very seldomly, but it's possible. Another example, let's look at 2 standard errors above the mean. We know that this is going to happen about, half of 5% by the empirical rule, and more precisely about 2.3%, 0.0228. What I'm illustrating here is that this is the likelihood of sample means falling out into these tails given a population mean equal to that hypothesized value. So it's possible to be out there, but we know the likelihood of being out there, okay? And in these two cases, it's fairly low. So these tails, right, that divide this distribution in the left-hand side, the 0.0013, and on the right-hand side, 0.228, these can be likened to these critical values that we discuss in this slide. So we're going to choose critical values, okay? These are going to be thresholds. And if the sample mean is outside either of these values, this is for this two-tailed test, then we're going to reject the null hypothesis, okay? And if it's not outside, if it's within these bounds, then we fail to reject. So here's an example where my critical value is 1.96. You should remember from the confidence interval construction that corresponds to a 95% level of confidence. That's my critical z value. And you can see that these are threshold values. Any x bar that falls out here or here is where we're going to reject the null hypothesis. We're just saying that we know it's possible, okay, but we're going to say that we won't attribute getting an x bar of these values to chance. We're saying that there's something structurally different regarding the population mean, right? That it's different from its hypothesized value. Now, we could be wrong, and we know we'd be wrong about we would be wrong about 95% of the time here, right? If we're 95% confident, that means that 95% of the data are going to be around around 1.96 standard deviations above and below the mean, and 5% of the time we're going to be in either of the two tails. So you can see we'll reject a true null hypothesis about 5% of the time. So that's important. We're allowing ourselves 5% of the time to potentially draw a sample from the population, calculate X bar, and reject the null, even though the null is true. So choosing a critical value is the same thing as choosing the probability of it making a type 1 error, because if you remember from last time, a type 1 error is rejecting a null hypothesis that's correct or true. So alpha is the level of significance, okay? And alpha is also the probability of a type 1 error. What chance can we live with? You know, what do we want to constrain alpha to be? The typical levels are 10, 5, and 1 that correspond to 90, 95, and 99% confidence. With, by and large, the 5% or the 0.05 alpha being the most frequent, the 95% confidence level. So sample data must result in a sample mean that lies outside of these critical values in either of the tails for us to reject a null hypothesis. We're saying at that point, it's no longer attributed to chance. A multiple choice question here. If a test of a hypothesis has a type 1 error probability, alpha of 0.01, we mean if the null hypothesis is true, we blank at 1% of the time. When we know a type 1 error is rejecting something that's right, or rejecting something that's true, and so it'd have to be, the answer would have to be B here. So let's put the steps together to completing a hypothesis test of a single mean. We're going to state the null and alternative hypothesis, okay? We are going to estimate the things that we don't know, which could be, which will certainly be calculating X bar, sample mean, and it also could be calculating the sample standard deviation in the cases, which would be most realistic cases, where you don't have a measure or a value for the population standard deviation. You'd also have to estimate that with S, the sample standard deviation. Given alpha, we determine the critical values. These could be T or Z. Remember, they would be T if we don't have the population standard deviation and we had to estimate it using the sample. That's when we want to be more conservative and use T in place of Z. We want to calculate our test statistic. Again, this will be a T or Z for the same reasons. And the test statistic is going to tell us how many standard errors, right, standard deviation of the sampling distribution, is X bar from the hypothesized value. How many standard deviations is X bar from the hypothesized value? We're going to compare the test statistic to the critical value, and then we're going to write out our conclusion. Okay? This is just isolating what I mentioned before. When you're doing an analysis around the mean, either in the confidence interval world or the hypothesis test, if you have the population standard deviation, if you have sigma, then you're going to use Z. Okay? But if you don't, and this is case 2, and you have to estimate that population standard deviation through S, the sample standard deviation, that's when you want to use T in place of Z. It's the more conservative estimate to use. So we have an example here of the Boone, in Boone, North Carolina, Brewing Company. The BBC claims that their pints of beer average exactly 16 ounces, no more, no less. So a stats student, 21 or over, of course, legal drinking age, is skeptical. All right, the student decides to test whether the average pint of beer at the BBC is different from 16 ounces. And remember, our research question is what we're going to frame in the alternative hypothesis. So we should be seeing that different from sign in the alternative. All right. For this particular example, because I want to do one where we know a population standard deviation and use Z, and one where we don't and we use T, we're going to know that the population is distributed normally and the population standard deviation is 1 ounce. That's going to allow us to use Z. The null and alternative hypotheses, very simply, you see that not equal to sign in the alternative. Again, that's my research question framed in the alternative. And the null is the status quo, right? The benefit of the doubt that 16 is the average ounce of a pint of beer. And notice again, H sub naught and H sub A as the relevant subscripts. Okay, and this is ounces. We have to take a sample and calculate the sample statistic. Okay, so in this case, the student is, let's say, strapped for cash and can only afford to sample 12 pints. So we have a very small sample. But we realize that this sample size is sufficient to assume normality of the sampling distribution. And the reason is the earlier assumption in the previous slide that the population itself, the population of ounces in a pint of beer, is distributed normally. So any sample size would be sufficient. Okay, if I didn't have that caveat, that assumption, then we couldn't assume normality of the distribution of sample means. So the student takes the 12 pints, here they are, right? Legitimate pints of beer, measures the exact ounces in each, and this data is listed in a column in Excel. Okay? All right, so this is our data set. These are the 12 ounces of beer. I'm going to go and open my Excel file, and you can see that the sample mean, the average, right? I'm just using the average formula here, is 15.88 ounces. Okay? So I'll take that and copy and paste it back into the lecture slide here, and that's going to be X bar. Now, given a significance level, we can find critical values, and we're going to use a significance level of 0.05, which of course corresponds to the 95% confidence level in this result. So our two-tailed test, we have a critical value in the positive realm and a critical value in the negative realm. All right, 1.96 and negative 1.96 are my Z's. Now I need to calculate the test statistic. All right, so I'll take out the pen here, and we know that this Z, and you can see that I have stat as the test statistic subscript, 15 point, let's see, what was that sample mean? 15.88 to 2 decimal places, ounces relative to the 16 that is hypothesized. We have 1 standard deviation, 1 ounce, divided by the square root of my 12 pints. Okay? And I'm getting negative 0.416. All right, so negative 0.416. We have our critical Z values of 1.96, the fail to reject region, the rejection region, and negative 0.416 falls right here. That's my Z stat, right? And since, and one way to write this is in absolute terms, because it's a two-tailed test, right? If the Z stat and the absolute term is less than Z critical, right, then we fail to reject. Right, and that's what's happening here. 0.416 being less than 1.96. So we fail to reject the null. Let me write that in here. We fail to reject the null hypothesis that the pints of the beer and the brewing company are on average 16 ounces. So we're finding evidence in favor of the fact that the average is 16. All right, even though X bar right, was 15.88, right? We're saying, we know that this is different. We're attributing to sampling error that this is just, we're allowing that this is due to chance, right? Due to the fact that we're taking a sample from the population. If this was far enough away, if this was farther than 1.96 standard deviations, outside of that 16, then we would say we're rejecting this. We're not going to attribute it to chance. Okay. Let's look at another example. The average GPA of College of Business students. Okay. Suppose the national average GPA for business students is 3.05. And using the sample from a particular class, I'm interested in testing whether the average GPA at App is different from 3.05. And so App is the university here. And constructing the null and the alternative, the different from language, again, my research hypothesis is trying to see if it's something different from that national average. Okay, that's my research interest. I'm going to take a sample and estimate population parameters. So suppose I randomly sampled 30 students, okay? And the question of why at least 30, well, when you don't have information about the shape of the population data, then 30 is just sufficient to appeal to the central limit theorem, right? The central limit theorem says that regardless of what the population looks like, right, the central limit theorem says that if sample size is 30 or more, your sample mean is going to come from a normal population, a normally distributed data set. Okay, we don't have measure here for the population standard deviation, so we need to estimate it using S, right? S being the sample standard deviation. All right, and this is where you use T in place of Z. We don't have sigma, we have S. Here are the results from using descriptive statistics in Excel. The mean value of 2.94, okay, that is different from 3.05, but the question is it different enough from 3.05? Can we attribute it to chance, or can we attribute it to something that we're finding evidence that the mean is different from 3.05? The standard error right here, 0.0907, is S divided by the square root of n. Okay, S being this value, 0.4967, divided by the square root of 30. All right, but it's all figured out for you. And so really, it's these two values that we're going to need to construct the test statistic to compare to the critical value. So we are going to maintain that same level of confidence, 95%. So alpha is 0.05. That's type 1 error, right? That's the probability of making a type 1 error. And we're going to be using T here. And with a two-tailed test, our critical values will follow 29 degrees of freedom. And I encourage you to look on the table. 29 degrees of freedom and an alpha of 0.05. With a two-tailed test, we have T of 2.045 and its negative value, of course. The test statistic is, let's see, what was 2.9, okay. We'll carry over these values here. 2.9437, 4 decimal places, relative to 3.05 over 0.0907. That's the standard error. And that is taken from the descriptive statistic measure in the previous slide. And I'm getting negative 1.17. So 1.17 standard error is below 3.05. And is that far enough away for us to reject the null hypothesis? Well, the answer is no, right? Here, my rejection region is here. And here, in my test statistic negative 1.17 is right here, right? And so I'm failing to reject the null hypothesis. Finding support in favor of the null hypothesis. All right. And at the 0.05 significance level, we failed to reject the null hypothesis that the average GPA of stats 2 students, or stats students, I think was the original question, is 3.05. So again, we find evidence in favor of the null.